I think it's the debate side.
Hi, Gerd, this is Tom Brown. Can you hear me? I think you're muted.
Correct. Hi, Tom. Hi, everybody.
Okay, very good. So I'm gonna introduce you and then you can go ahead and try sharing your screen if you like.
I have a lot of noise in the background.
Well, we will mute so that you won't have so much noise.
Okay. Now it's silent. Now I don't hear anything.
Could you do a sound check? I thought Jared said he can't hear us. Can you hear us, Jared?
Yes, yes. Now I hear you.
Okay, good.
So I think we have a quorum here. This is our first colloquium of the year. Welcome. And Gerd, I know you're connecting from a great distance, but among our group here are a record large entering PhD class. So we're welcoming them as well to our first colloquium. In fact, just so everybody else is aware, if you're a first-year PhD student just starting at the Institute of Optics, could you just raise your hand briefly? You can see who you are. It's quite the group, so welcome. So it's my pleasure to welcome Gerd Leuchs here for our first colloquium. He has a long list of credits and accolades to his name. He originally studied physics at the University of Cologne and Munich. He has spent time in the USA and Switzerland. Most recently and for quite some time, he's been a full professor of physics at the University of Erlangen-Nuremberg in Germany. And he's also been, since 2009, he was director of the Max Planck Institute for the Science of Light. And I my personal connections with Gerd go back to, well, quite a ways, but around the year 2000, his research group and mine independently both started studying some of the intriguing characteristics of tightly focused beams that have azimuthal polarization, radial polarization, and so forth. And I think at first neither research group knew the other was working on it. But then we, of course, discovered that quite soon. And it's been in some ways is a much more far-reaching and interesting subject. The title is "What is Quantum?" and I think he's going to explain what he means by the question, as well as perhaps the answer.
Yes. Yeah, to share my screen. Here we go. Share. So, yes, and you might not tell from the title, but cylindrical vector modes will play a role, believe it or not. Okay, so what is quantum? I mean, the small specifier here is in the sense of the second quantum revolution, that is when you deal with single quantum systems, which means it's not refers to when you look at large ensembles of quantum systems. So this was the second quantum revolution refers to. So we are about to write a paper, or we are in the middle of drafting this, and we, that is together with my good friends and colleagues, Natasha Korolkova from St. Andrews in Scotland, and Luis Sánchez-Soto from Madrid in Spain. So, why does it not proceed? Okay, here it does. So up here you see a question. It's a bit awkwardly written. So does the type of differential equation determine whether a system should be classified quantum or classical? The answer is no, as we will see. So here is famous Schrödinger equation. Here is the wave equation for light. Here is a one-dimensional differential equation that describes water waves. Here's a Klein-Gordon equation. There are 2D Schrödinger equations, which are the paraxial Helmholtz equation. But all these are differential equations, and they are mathematical. So you can give them to a mathematician and ask them to come up with a solution. And you don't need to tell the mathematician, watch out, this is classical or this is quantum. For the solution, it doesn't matter. Actually, when some of the mathematician I learned, I think they are more comfortable in proving that there is a solution and not so much necessarily to finding the solution itself. But this is a side point. I like my friends in mathematics. So the second question is the evidence for a superposition, is this sufficient for classification of quantum? And we know the answer is also no. Superposition can be for a single electron, but you also have superpositions in position space, in waves, when it doesn't matter which kind of waves, it can be classical waves. So we know in all waves, so including electromagnetism, we can have superposition. And then the interference pictures look very much alike. So superposition by itself is not specific for quantum. So then the third and last question of this type is evidence for entanglement sufficient for a classification as quantum? And entanglement is nothing but a more complex superposition when you have like 2 electrons at least. And that already seems to indicate, since superposition is not necessarily just per se quantum, maybe entanglement is also not. And this had been a debate. There were people talking about classical and quantum entanglement. Some people don't like it. So on the mathematical sense, instead of entanglement, because this is kind of like a physics notion historically, one should probably say non-separable state. So you can have these in the discrete domain, make it with 2 electrons with spin up and down. That's a state that you cannot, is not separable, as you cannot write it in a product state here. That is what also is referred to as entanglement. Or you can, in the continuous variable regime, where I come from, with squeeze states. So these are four four phase spaces or four modes. This is a beam splitter. So if two squeeze states come in, they span because of the phase shifts at the beam splitter. This will span big uncertainties on the two outputs. So this is also an non-separable state. So probably this by itself, some non-separability is also not necessarily quantum. So, and this is true as long as you don't specify what the measurement is. So in my talk, the measurement will play a big role. And I think my intermediate summary, and yeah, I mentioned this classical entanglement. I'll come back to that later. Oh, here's the note I wanted to make. What the differential equation, they don't tell you what the physical nature of this wave function is. And if you ask for what does it mean, the wave function, then this is closely related to the measurement. So this, it took a while historically to understand this, and I think it was Born who first kind of had the idea to link psi modulus squared with the probability to measure something. So this is Born's interpretation of the wave function. So this aspect, the physical nature of the wave function, this is nothing that mathematicians will tell you about. So here's my intermediate summary after the short introduction. And so if you ask, should we call a particular system quantum or classical? Typically not, I would say, because the proper description of one and the same system, whether you can describe it with a classical model or with a quantum, or whether you have to use a quantum model, which is incompatible with a classical description, that depends on the measurement you do. So for one and the same system, depending on the measurement you do, you can either get away with a classical model or you have to use a quantum model. Or maybe there is a system where you cannot think of any measurement that ever gives you for which it is necessary to do a quantum description. This you can also have. So measurement. So when you compare mixed states or thermal light versus pure states, so this could be maybe interesting. So for pure states, you have typically quantum uncertainties. So this could be an area in phase space. Thermal noise is more something that actually fluctuates in time. So typically quantum uncertainties, these are uncertain areas, and there's nothing that fluctuates in the mathematical differential equations that you are solving and when such an uncertainty comes out. Whereas in a thermal system, you have something intrinsically changing with time. But you see here this little blob that's even in thermal systems, you could argue maybe it's an underlying quantum system where some parameter is stochastically moving around. So you might wonder, maybe there's a little bit of quantum in this thermal noise, then that is also an interesting question. Now, when you do a measurement, then if you measure the thermal noise, you get a trajectory that looks very much like the trajectory that was there before the measurement. But in the pure state, you have no trajectories before, you just have this uncertain blob. And measurement, actually I should specify here, this is when you do one measurement, you get 1 point, then you repeat the measurement and you get a next point, and then you connect these points and you'll get some erratic motion that looks like a fluctuation. So the measurement turns an uncertainty into a fluctuation, because fluctuation, I think we all think of a fluctuation as something that varies with time. So the uncertainty doesn't vary with time, but if you have identically prepared systems all the time, and you do measurement, or if you have a laser and you have measurement time, you identify measurement time intervals, and then a new light is prepared in the laser all the time, and you do a measurement in the first time slot, then the second time slot, and the third time slot, and then you get different numbers, and it looks erratic as the fluctuation of a thermal state maybe, but the fluctuation here has been brought to you by the measurement and was not necessarily there before. So that's the difference. So because of this measurement, the predictions of quantum theory are probabilistic, and one some physical action, something that happens at a time. So the more abstract word projection is preferred by many. So since this measurement process has to do, kind of brings in something that looks like fluctuation, the stochastic element. So there was this attempt to explain some of the properties of quantum system by classical statistics. And if you are successful in doing this, of course, it's a classical model that explains what you see, then you don't need a quantum model. And basically all these theories that talk about hidden variables are such classical statistics models. But as we know, hidden variables do not always work. So there are some systems where such classical models not necessarily do not work. So how to identify the quantum behavior? Probably you need more than one measurement. If you have a single measurement, it looks like a classical stochastic process, as we will see. So in the following, I will look at different scenarios. The first one will be a system where we do a single measurement. And we look at systems where we would normally think these should be quantum. And you do a single measurement, of course, as usually, you identically prepare the system many times and do the measurement many times so that you get some statistics. And then we look at a system and do one measurement. And then we identically prepare the system and do a measurement which is kind of not compatible with the first one. So we say we measure two conjugate variables. So typically they are like Fourier related, they span phase space. So we do two different measurements, but not on the same system, on identically prepared systems. And then this kind of set of two measurements we repeat many times. And the third one is doing two measurements on one and the same system, one condition on the other. And that, of course, you repeat many times. This is always the same. So let's do this. Let's go to point one. So single measurement on a system one would normally think of as being quantum. So the one I like a lot is where you have a single photon, obviously quantum, you put it on a beam splitter. Then you have two click detectors on the two output ports. Then we know the photon, we usually say the photon can only be transmitted or reflected. So this one detector will click and not the other, or the other will not will click and not the one. And but this, so basically we prepare the system, we do one measurement, that is we have these two detectors and we look which one fires. So this is like one measurement. And this we can explain with a classical stochastic model, no problem. We don't need any quantum theory for this. So we could think of the beam splitter as being a stochastic element. So such a classical model will work. Although we know that a beam splitter is not really deterministic. It's kind of like it couples two modes in the case of optics. So basically it does a basis transformation. So it's the action of a beam splitter is unitary. So there's no stochastic element in the beam splitter. And what is really stochastic is the projection associated with the measurement, what we already talked about. But if you have only this one measurement, you can explain this by a classical model. Of course, as soon as you have a second beam splitter, bring these two beams together, have a second beam splitter and put it together to form an interferometer, then you don't get away with this simple classical stochastic picture anymore. So these classical stochastic pictures that work on systems which should be quantum, typically their validity is only very limited. And the second example of this type is the emission. So now you have a photon coming out, you have a detector. Let's see, it's a detector that has a very good time resolution. Then we do the measurement, we register when the detector clicks. Of course, we prepare the atom in the excited state, and that defines time zero. So maybe we use a very short laser pulse with a pi pulse that brings the atom with certainty into the excited state. And so we know at time equals zero, it's in the excited state, and we wait for the photon to come out. And when we do this, we all know what happens. This detector will give you a click at some point. Of course, at a time larger than zero, because you won't see the photon before you put the atom into the excited state. And then you identically prepare the system again and repeat the measurement, and you get a click at another time. And you continue this. And eventually, when you do a histogram, you see an exponential decay. And so the words like spontaneous emission, mean lifetime of the excited state, these are all terms that are lent from statistical language. And so because this looks very statistical, but we already know maybe this stochastic part is the measurement itself. Anyway, so from this picture here, we might think, oh, a single photon is very short in time. These are very small peaks here with a width of delta, like the width of this red line here. And so I can use a stochastic model, and the stochasticity describes the behavior that these photon clicks are distributed statistically with this exponential envelope, with this probability. Okay, let's go to, I said this already, okay. No, this I didn't say. So when we do this experiment in different ways, for example, we find a way to build the detector with a better time resolution, then suddenly these photon peaks will become smaller. So the single photon, quote unquote, that we measure here, these red peaks, they are as short as the time resolution of the detector, as short as the detector can measure. So this width seems to be a property of the detector rather than of the photon. So you might want to wonder, but you can also not wonder about this and just use this classical stochastic model. So next, I think now we come to point 2. Yes, now we do 2 measurements, but not in a sophisticated way, one measurement and another measurement conditioned on the first one, but we identically prepare 2 identical systems and do a measurement with one conjugate variable on one and the other conjugate variable on the other. So these mutually exclusive variables are measured on these two systems, and then this whole thing is repeated many times. So let's take a laser. So when we have a laser and put it on a direct detector, then we see boson statistics. So this is supposing that the detector can resolve single photons, and some traces like this appeared in the literature as early as the early 60s. I think Tito Arecchi in Italy was the first one to produce such a picture by photographing an oscilloscope trace. Anyway, this is what you see. So this is typically Bosonian statistics that describes the photons coming out of the laser. And of course, you can describe this classically. You just need a classically stochastic model so that the amplitude or the intensity of the given by these photons, so there are all these clicks and they're jumping up and down. Also, the intensity is kind of like shows all these peaks. But you can also do another measurement. You can split the beam, put it on 2 detectors, and then looking for the correlation function, the intensity correlation function of the two. And if you do this for a laser, I forgot to do this here. So this detector and this detector, the outputs are multiplied and averaged, so to say, by multiple. And if a stochastic signal like up here, you typically expect a peak at time equals 0, and then some decay to some lower level at larger times. But for the laser, so for a pure coherent state, if you manage to get a close to coherent state out of the laser, you will get just a flat line. Of course, you can model this also classically, but with a field which has no fluctuation at all. So this is really contradicting. I mean, here I need to have a largely fluctuating field explaining these Poissonian statistics of these peaks. And here, if this were really one-to-one true, we would expect a completely different intensity correlation function. This is mutually exclusive. So from such measurements, you could say, I need to really change the classical model, and this is not compatible. I want to have one model to describe the different things I want to see. So maybe I need a quantum description. And the second example, oh yeah, this reminds me, was Dmitry Strikalov. We put this in a paper, in a review. So the second example is the one that we had before, but I'll now expand on this. So before we looked at a detector, looking at the emission, spontaneous emission of a photon from an atom, and which was had good time resolution. But we can also use a spectrometer, so a detector that has frequency resolution, and that's also possible. When we do this, we plot the intensity now as a function of frequency, not as a function of time. And if you do this experiment, the first emission, first photon will also give a click. And then another click, and so on. And then the envelope, the histogram, will be a Lorentzian curve of width 1 over tau, where tau is the decay constant of the envelope here. But this, so I can, both of these separately, I can describe as a classical model. I mean, describing this statistical peaks that I see in these 2 experiments. But when I take this seriously, as I would do in classical physics, saying, oh, if this peak is so narrow, this must be the width of the photon, then such a narrow peak, since the photon is ultimately a wave packet, the spectral width has to be correspondingly broad. But the spectral width that we observe is much narrower than 1 over delta. So this is also not compatible. So from only measuring the time resolved intensity or the spectral resolved intensity, we could not rule out a classical description, but doing both of them, we can rule out a classical description if you want. So then the last example, 2 measurements on one system, one conditioned on the other. And so this is like the famous Bell test. So quantum entanglement requires unseparable multidimensional wave function and 2 measurements on one system. Possibly, but not necessarily at distant locations. And then you check for the correlations. So basically what you do is you have a source. If you're in optics, I mean, this is true in general, but if you're in optics, maybe you have a photon pair source and they are entangled, whatever that means. And then you have a one detector measuring one of the members of the pair, and the other detector measures the other member of the pair. And so the detector is basically typically then a combination of a filter and an actual detector, so that you can look at different components. So it could be a polarization filter, for example. Now what you do is you look with different filter positions, different angles of the polarization filters. For example, you look for correlations. So you're looking for correlations between two measurements. And this is how the Bell test typically is done. So in the second measurement, so you do one measurement, and the second measurement, the possible outcomes are reduced because the first measurement already kind of gave rise to a projection. And so this is a special situation when you have these. So if the correlation is not describable by classical stochastic model, a classical stochastic model would be like a hidden variable model, for example, or this quotation should be a bracket. I'm sorry. Then this should be quantum, and that relates to the violation of Bell inequality. And the requirement for something like this to observe is that the total wave function is not separable. Then people say this is non-local. So with local and non-local, I have a little bit of, so I think this is not so precisely defined. I don't like this term so much, but I mention it here because this is what people call it often. So I basically know what they mean, but I think for me, this is not as quantitative as I would like to see it. Now we can ask the question, what is this? I mentioned this notion of classical entanglement. So this is also some function describing the system, which is non-separable. And so classical entanglement, there you have non-separable multi-dimensional mode function. But you don't, so in these typical situations, and I will show you some, what you do is you do not correlate two measurements, you correlate a filter process and a measurement. And then even the mode function, which is non-separable, like such a radial polarization, Tom Brown mentioned that his group and my group independently found some interesting properties of such cylindrical vector modes. When you write them in terms of products of the higher order modes and the polarization, you have horizontal polarization and TM01 plus vertical polarization and TM10. So this is a non-separable mathematical function, but it's a solution of Maxwell's equation. It's, I mean, you cannot say is this quantum or not. I mean, you're not even talking about the excitation in the mode, but it's non-separable. And in such non-separable mode functions play a role in this classical entanglement. So typically what you do is you have two filters, like in this measurement of the quantum entanglement before, but you have only one detector. So you have one filter and you measure what comes through. So the first one, it's just a filter process. And the second one is a filtering process plus an intensity detector. And together they are a measurement of certain components which are filtered. The filtering by itself, like a polarization filter, is a unitary operation. There's nothing stochastic associated with it. It's only this detector that leads to a projection. A filter by itself does not lead to a projection. It just separates functions, but nothing gets lost. When you do a projection, you lose some information. So this is qualitatively different. And this is basically the point I want to make, that when so with such a system here, you cannot possibly detect whether something is quantum or not, because you only do one single measurement, like in the first one here. So this is not enough. Nevertheless, I forget what was next. Oh, yeah, and you look for a correlation between this filter and this filter. These typically have like described by angles. And so basically when you do this, if you correlate not two measurements, but a filter process and a measurement, you'll go back from 3 to 1, only a single measurement. Okay. So yes, so this we discuss with Natalia Korolkova, and I will discuss this in this report on progress in physics, but it's a longer paper. We want to kind of put this down, or more specifically in this new manuscript. So now I want to discuss two papers where to violate something like a Bell inequality. So Antonio Zilaquet Curi from São Paulo, when he put the paper in, he called this a Bell inequality for spin orbit separability of laser beams, and the violation of this inequality. And the referee insisted it should be Bell-alike inequality, because he was a bit that's fine. So this is now this is the title. So he was using exactly this cylindrical vector mode. This is the mode function TM 01010, and the E here is the polarization, if I remember correctly. Yes, this is the R dependent, so this is the mode function. And so there's a source, and here you can see this is a superposition of the TM01 with one polarization and the TM10 with the other polarization, and out comes a radially polarized mode. And here we have many detectors and everything, but what you are correlating, so this is the mode, what you're correlating is a filter here, this beta, this angle, this is kind of rotating the transverse spatial mode, yes, prism. Angle. So these two are correlated, and then it goes through first one and then the other, and then you analyze this, and you have many detectors just because you analyze, I think they look for Stokes variables here, so you need several detectors, but basically it's one detection. So it's one filtering process, another filtering process, and then detection. So this has nothing to do with, this is not a setup with which you can prove whether something is quantum or not. But it still can be useful. I mean, it can be useful properties. These can be useful properties for some applications. And so this is here is emphasizing. First, you have a filtering with this angle beta, and then a measurement process in combination with a second filter, which is determined by this angle alpha, the half-wave plate. So then there is a second experiment I want to discuss with you. This is from your place, Joe Aberle, John Howell, when he was still in Rochester, and I think Xiaofeng Xian and Bethany Little must have been students. I think I don't know them personally. And so this is really down to the essentials. So I like this a lot. Joe Aberle said, look, when you talk about this non-separability, you can go down, I mean, to the simplest, most basic case. You just have unpolarized light. X and Y are the polarizations, and EX and EY are stochastic functions. So they are uncorrelated. And so if you, so these are big blobs. So there is a source to create this, and then they did the measurement, and then they look at this with different bases. And if you look in different bases, you have some component from here, and so you can also see some correlations because you mix this and you do this in different bases. And on the experimental side, there was a challenge, because such a filter function like this half wave plate here with the angle alpha, or like this. Is it a Dove prism? I think it's called Dove prism, which rotates the transverse mode function. This is readily at hand, but here these are the temporal functions, and to have something like a more abstract rotation, a variable linear combination between the two, this is not so easy, and that was one of the challenges there, but they solved it. And then when you look at it, you have here a first filter process, and then you have so this this is a way to kind of filter the mode function. B doesn't appear here, but it has to do with this with these objects here. So in both these cases, you are correlating the angle of a filter operation and the angle of a measurement, which is a combination of a filter plus an intensity measurement. Not what is required to do quantum entanglement. So there is another paper from Rochester involving also Nick Vamivakas and Joe Eberly and John Howell and many others. Oh, Miguel Alonso is also there. Yes, now I see. So there, this is a citation from the paper that participation of several degrees of freedom is almost every imaginable optical participation. So optics is very rich. You have many degrees of freedom, and these appear in many optical situations. And there's myriad of relationships possible among the participating degrees of freedom. And this is the foundation of optical versatility. And the effects are interference, polarization, coherence, complementarity, and entanglement. And some of them, I mean, they have to do with this classical entanglement, and some can be real quantum entanglement. But in order to prove this, you need to do different measurements. You need different projection processes, not one projection, which suffices. And so I told you that nevertheless, these classical entangled systems can be helpful. And one of the experiments that has been done came from my group some years ago. So this was the PhD thesis of Stefan Berg-Johansson. It's again using this radial polarization mode. And so this entanglement means that there is a correlation between position space and polarization. So when you want to measure the position of an object very quickly, you have to have a camera, which is very quick, but the camera has many pixels and you have to read it out. Typically, there's a problem with camera speed. But here, basically, you get away with a single camera measurement. So you have different detectors, because here you have to measure the polarization. So you have to measure Stokes parameters. So if you want to get two Stokes parameters, like two linear polarizations, for example, you need altogether 4 detectors, but they kind of fire at one time. And so if the object obscures a little bit before everything is unpolarized, it appears unpolarized, but if it blocks something out, you will see a little bit of polarization. And basically from there, you can get the trajectory. So there's a comparison of the actual trajectory and the inferred trajectory. So this fits quite nicely. And of course, it's much faster than any camera. So it's kind of entangled, or at least non-separable, but has nothing to do with quantum, but still very useful. So the various scenarios are these 3 that we discussed in detail. The first one is not enough to tell whether something is quantum or not. The second and the third, at different levels, they kind of can tell you a classical description does not suffice. So basically in nature, I mean, I think nature does not distinguish between classical and quantum anyway. It's us that we wonder whether our more simple classical models can work. So sometimes they work, and for the same system, sometimes they don't work. Basically, when we go from quantum to classical entanglement, we go back from 3 to 1. So here, now I will discuss two papers more on the theoretical side with Luis Sánchez-Soto, with whom I enjoy collaborating for many years. So this is great fun. So in this paper, he compared the different measures of quantumness, quite a number of them. You'll see the list here, and this is for a single system. So this is nothing where you could look for entanglement. Because for entanglement, you need like at least 2 dimensions, because you need to measure 2 different things. So this is a single one-dimensional system, like a single mode, for example. But you can have superpositions, of course, and they can be quantum, as we discussed. This is point number 2 in this list of 3 before. And so if I'll just pick out one here, the Husimi extrema. So the maximum value attained by the Q function is in a sense a distance measure for pure states. And the Husimi function, this is a phase-based distribution function where the way to measure this is to take a signal and split it. Of course, there's a penalty because you have some quantum noise entering in the other port. And then you basically have then 2 separate systems, slightly deteriorated because there's additional quantum noise here. But then you can measure conjugate variables separately, X on one and P on the other, the 2 variables that span phase space. So in the experiment, of course, you need local oscillators, and to pick one and the other, the 2 local oscillators have to have a phase which is different by 90 degrees. And so this would qualify for point 2, because I basically have 2 identical systems where I measure the conjugate variables. And then this measure for coherent state, squeeze state, Fock state gives all kinds of different numbers. So you can compare this with all the other measures for a single system. But for the entanglement, more important is to look at higher dimensional systems. And this is another paper also led by Aaron Goldberg. So I very much enjoyed working with him. So, and here we were focusing on so-called symmetric states. So this is in the Fock state basis. So there is 2 dimensionals, like 2 modes, and the wave function is the symmetric state is that you have n photon in one mode and 2s minus n photons in the other. So this is the symmetry of the state. So not all states are like this, of course. So now if you think more about what does it take to detect entanglement. So when you have a higher dimensional system, so that you can do one measurement on one of the subsystems and another measurement on the second subsystem, then one talks about the total system is partitioned in 2 subsystems, but you can change the basis. So in optics, this is most obvious for optics. You have two modes, and with a beam splitter you can mix them, and you have 2 other modes. And with electrons and massive particles, in principle, mathematically you can do this too, but these are kind of like awkward looking objects sometimes. So these things are easier to think of in optics. But what it tells you is that one and the same system, by describing it in different bases, it looks different. And if you then have different subsystems, if you partition your system in different types of subsystems, if you do their measurements, then it can be that in one particular partitioning, you don't have entanglement, and the other one you have entanglement, and this is typically always the case. And so such mode transformations, which is like a basis transformation, this can alter the state, the state of the system. I mean, without changing the state, but in the description, it looks entangled. In the other case, it looks separable, non-entangled. So whether something quantum entanglement is not only a property of the system, is not straightforwardly a property of a system, but it largely depends on the partitioning you do. So for example, in optics, you can do Hong-Mondel interference. You put in two photons. This is a product state. Then you use a mode transformation, and nothing else does a beam splitter. You put it on a beam splitter, and out comes 0-2 mode formation introduced by the beam splitter. You go from non-entangled to entangled. So this kind of is what I mean. So the question was, of course, there are some systems you can do what you want. You never find anything that looks quantum. So these are very classical systems. Maybe should still be possible to kind of do some qualification about how to do this. So the idea was, what about averaging over all possible physically relevant modal decompositions? Everything that is possible. If you then average over this, this could be a property of the system by itself. Because if you only use one modal decomposition, this what you measure, what you characterize is this system with this particular modal decomposition, and if you change it, you will get a different answer. But if you average over all possible modal decompositions, that's a different story. So, for example, one measure is the linear entropy of reduced density matrices. So this is 1 minus the trace of the the reduced density matrix, and then like integrating over all different modal transformations. So the R refers to this modal transformations. Then you get this average linear entropy, and the measure of averaged entanglement appears then as a sum, as is shown in this paper, of multiple moments of a state, and as SU2 covariant. So you can plot this on a Poincare sphere. This is how you describe the SU2 group, and so basically we now can connect quantumness to geometrical properties, and the problem appears to be closely related to distributing points over the surface of the Bloch or the Poincare sphere. So symmetric states which maximize this entropy are these states depending on the dimension, depending on S. And so when you write down theoretically this averaged entropy, so then this is a sum over the different dimensions, and so 2s is the number of zeros of the wave function, but then also of q, and so basically you have two s points here on the sphere, which refer to the zeros, and in order to be maximally away from a classical state, so the most quantum, you have when you distribute these zeros as isotropically as possible over the sphere. So this, I think, is a very nice result. Okay, so this brings me to the end of my talk. So the final summary is that the characterization as quantum cannot necessarily easily be done for a single system without specifying which measurement you do. And this goes both ways. You can have a system which should really be quantum, and may appear classical, provided a proper measurement is done, as I've shown there. Or you have a system like a thermal state in a mode which is clearly very classical, but still deep down, maybe it's a quantum state which is where just one parameter is varying largely statistically, thermally, as a function of temperature or maybe stress from outside, which is varying. And so maybe if you do the proper measurement, you can still find some quantum property which you can dig out from this more classical fluctuation. And this is a challenge, but some people think about this in quantum key distribution, where often you have the problem that when link from a customer to the machine with microwaves or something, you are far away from pure quantum states. It's looking more like this. So the idea, if you could do something to dig out this quantum, you could probably still use this quantum security that you want in for key distribution for secret exchange. But that's something which is in the future. But that would be an example where you have a system which looks very classical, but if you do the right measurement, you can probably still get some quantum aspects out. So, and the final message is, again, basically, without doing two measurements in one or this other way, one of the two ways that I described to you, it's really difficult to quantify the quantum character. Basically, these two measurements, one way or the other, is needed. And with this, I think the next slide says thank you. Yes, it does. Thank you very much for listening. Are you still there?
Yeah.
Ah,
Thank
okay.
you very much. Thank you very much, Gerd, for this nice talk on what is classical and what is quantum. And I'm a little bit confused at this point. So when should I call something quantum? I'm not totally sure. But
Yes, it's not so easy. That's perfect. That's perfect because it's not so easy. Yeah, one has to think about it. Yeah.
Right. Yeah, right. All right. So I think with that, let me open the floor for questions.
Yes,
People
sure.
who are sitting here in person, they can ask questions right from here. And people who want to ask questions, the people who are online could either just raise their hand and ask a question when they see time, or they can put a chat and I can try to do it on chat. I can take a look at that. Okay. So with that, Joe, you want to go first?
You mentioned two of our experiments. That was very nice. One thing that we came up with, the question that referees had a hard time coming to grips with, was the question was what kind of light was used when we did those experiments with classical entanglement. We wanted to make sure there wouldn't be some confusion about whether the light we were using was quantum or classical. So we thought, now how will we proceed? Then we thought, wait a minute, what kind of light did Thomas Young use? Or Fraunhofer? Was he using quantum light or not? And then it eventually comes to thermal light. We realized all of those guys were using thermal light. And so thermal light seemed to be the best choice for us to use in those experiments. So we used the fact that lasers operating just above threshold are pretty close to thermal in their statistics.
Yes.
And that seemed to satisfy referees. But it doesn't answer the question that was being asked exactly. Now, the other point, before you react to that, let me mention another thing. You haven't mentioned degrees of freedom at all. And in my opinion, it's actually degrees of freedom that are being entangled. They can be associated with modes. modes can be associated with different degrees of freedom. So it's a difference in language. So this is really a question to you. Do you agree with that the degrees of freedom are satisfactory to hold in mind?
Yes. So the first one about the type of light. So when I think about it, I remember my little trajectory of the thermal light with this underlying coherent blob. So
Right.
I think if I look at a fluorescent light, which is more and more substituted by LEDs, but we know them. So there, I know there are individual atoms, mercury atoms, which are excited by electrons, and they're excited, and they probably send out single photons. So I think maybe there is a single photon. There are many single photon Fock states which are rattling around in phase space very erratically. All over the place. But this could be different from like an initial laser where something is changing, some parameter is changing so that you have a coherent blob which looks different from the phase space distribution of a single photon. And this is moving around. But if this thermal moving around dominates, usually you cannot see the difference. But in principle, there could be even a difference between thermal light, I think, but it's probably difficult. So if you only have a little bit, so if the thermal character is not much larger than the extent of a coherent state, so it's like so that the ratio between the orbit, this thermal orbit, and the extent of the quantum uncertainty is not so big. And then it's probably easier to look at this. So I'm wondering. So then maybe there are some questions one might want to ask. Now the degrees of freedom, I think maybe I didn't put too much emphasis, but when I was quoting your paper, I mentioned this, and of course also when you have this radial polarization, there are 2 degrees of freedom. One is polarization, the other one is the modal function, and there are many more. So I think there are different types of degrees of freedom. One is typically associated with mode function, but another degree of freedom is also the excitation. So basically, the way I think about it is that when you quantize light, you still need Maxwell's equations to tell you what are the proper modes or standing waves or the patterns in space-time. And then the excitations, they live in these patterns. And so you have this kind of excitation type of degrees of freedom, and then these modal function types of degree of freedom, where the transverse distribution and polarization is all part of it. And so for classical entanglement, typically you have non-separability between different types of modal degrees of freedom, and you get along with doing only one measurement. So you measure only one excitation, but in order to, so if you think that the typical quantum aspect is not in the differential equations that describe your system, but is in the measurement, then and the measurement is doing this projection. And if you're on measurement, you don't know that this projection actually is a projection because you didn't check whether it was projected. But if you do a first measurement and it leads to a projection of the system, and then you do a second measurement, then you are sensitive to the projection of the first. And so only then with the second measurement, you can quantify the projection. So for this quantum nature, I think these excitation degrees of freedom are more important. So you need to look at 2 of them. So I think, does that make sense?
Let me confuse the situation just a little bit more by mentioning that if only Thomas Young or any of the subsequent observers of optical properties had been able to measure the temperature dependence of their light, they would have ended up in, right? That's where quantum theory began, with thermal
Yeah.
light.
Yes. Yeah. No, that's right. Yeah. Oh, this reminds me, something that I only learned to appreciate. I mean, Joe, you know, I'm not so young anymore. I mean, you have seen me many years ago. This means I'm not so young anymore. And only recently I appreciated that Planck kind of put forward two different types of radiation laws. So one is this, you have the number of modes, and the energy per mode is h nu divided by e to the h nu divided by kt minus 1. So this was his first one, the famous one that everybody quotes. And a few years later, he recognizes when you go to the high temperature limit, kt, this is something I had missed, because when you do the expansion of this energy per mode, and you go only to the first term, you get kt. But at some point I noticed if you go, so if you expand the e to the h nu divided by kt in Taylor series, so you have one, the first term is a 1. So if you only do the second term, you get kt. But if you go to the third term, you get a contribution which is not temperature dependent, but is not vanishing. It's a constant term. It's 1/2 h nu. So this is the first time in literature. So this was, I think, in 1912. I think this is the first time that the ground state of the harmonic oscillator appeared. And then he suggested, this is really strange. It should be kt. So he added 1/2 h nu to his energy per mode that you had before. Of course, with infinite number of modes, you get infinite energy in the vacuum. So he discussed this problem, but he made the wrong conclusions. But this, I don't blame him for this. This was much too early. But it's really, you're completely right. When you look at these early struggles with thermal light, there's lots in there, and even the ground state of the harmonic oscillator appears in these first papers. And the year after that, Einstein and Otto Stern, who was a postdoc with Einstein at the time, they applied this to some anomalies of specific heat in solid states. So and they could explain this with this second radiation formula of Planck. So this is something I had missed for many years in my life, but it's all fantastic. I completely agree with you. People, by properly looking at the thermal part, people could have learned a lot. I agree.
Really good, interesting discussion. Yeah, you have a question?
I just have an interesting question. Do you think quantum entanglement is a result from a fourth-dimensional world? Or I mean, fourth-dimensional is spatial, so we separate the temporal axis. So I think because the entanglement can be beyond the speed of light, even in a very long distance, you can have quantum entanglement. So that's something. Do you think that's a result from a higher dimensional, a spatial dimension?
So I'm not completely sure I understand the question. So you can have an entangled state where the different parts of the entangled state are largely separated. And are you asking whether this
whether this is from also can be perceived from a higher dimensional world? I don't have
Yes,
other words for.
Of course, you need a higher dimensional Hilbert space to do this. But
Right.
yes, of course. But the question was not whether you can communicate faster than the speed of light, then, or not. This is
Right, you cannot actually communicate with that entanglement.
Exactly. Yes.
Okay.
Yes. Exactly. Yeah. So that was not the question. Yeah. Yeah. Right.
All right. I don't see any hands here. Anyone online wants to ask something? Any questions from people online? I don't see anything in the chat. If not, well, I think we can thank.
I have a question.
Anybody have a question? You have a question, sorry.
Are there any other examples for classical entanglement that you know of?
It
Examples
doesn't,
for classical entanglement?
doesn't.
Yes. So this one, this one state I showed you, this cylindrical vector modes, which Tom Brown, where Tom Brown and I share a common interest. So this is a typical situation. So you filter first the mode function, then you filter the polarization, and then you have one measurement, and then you can violate Bell's inequality. And this is basically what this Antonio Zillaquet has done. So this is, but then there are many different. I mean, I would be talking for 1 or 2 more hours if I would give proper reference to all of them.
I mean, look to me, anytime you take a polarization and something either in space or in time, you're dealing with the pulses in time and your polarization in degrees of freedom, which as you already said. If you have 2 different degrees of freedom, one is space and polarization, one time in polarization, you can construct examples of the classical entanglement.
So I picked out these 2 because I think Antonio Zillaquet was one of the first ones to do this. And then a little later, this work from Rochester, I think it was really kind of boiling it down to the essentials and say, look, even, I mean, you don't have to go to these complicated higher order modes or so. Just take a single mode, just have polarizations you can hardly avoid. So you have 2 polarizations, and then you have the excitation function classically, which is kind of stochastic. These 2 and that's it. This is not more what you need. So this was really going to the essential basics, and both theoretically and then also experimentally. You showed that this is also, I mean, this violates inequality, but of course it's no proof for quantum, as was stated in the paper completely correctly. But these were 2 examples which I picked for the reasons I just told you, but I could have used many more.
Okay, I see a question on chat by Seturaj. Seturaj, do you want to ask that, or you want to read the question?
I can read it. Yes, it is a hypothetical question. If one comes up with a phenomenon that can only be explained by considering the photon nature of light, not considering a statistical picture, then according to you, can that phenomenon be called quantum phenomenon? Well, I think so. So let me say the following. Often people say quantum entanglement has to do with non-locality, and a classical entanglement is local. This is what this is the difference. But for me, it is difficult to say what is local and what is non-local. So for example, hydrogen in the ground state. You have an electron and a proton, and their spins are in an entangled state, not separable. It's a singlet state. So one of the Bell states, if you want. But they are so close. I mean, this is really quantum entanglement, and maybe it's difficult to even measure the electron and the proton separately, but this is maybe an experimental challenge. But would this then be local or non-local? I mean, obviously it should be non-local, but they are so close. So this concept of local and non-local, I don't like so much. So I like much better to say, in order to, I mean, basically we need to do measurements to analyze a system. We can always talk theoretically about something and use a theoretical model and play around with this. But ultimately, when we want to relate this to nature, we have to put something up in the experiment or out in nature or whatever, or look at the stars or what, and do experiments and do some measurements. And so what I'm saying is,
All right, I think we need to we need to close this because the next class is coming in. So I don't know whether Gerd can hear me or not.